Go like that. There's a bit of reflection on that glass, so it's not. Okie dokie. Good morning. Good morning, folks. On behalf of the Centre for Climate Sciences of JPL, I'd welcome you all to this special seminar. We're running a series of special seminars. We're inviting kind of real-world experts in their discipline area to kind of give us a sort of a vision for what they think are the challenges going forward in their area of the science, earth sciences. And so we invited Sarah to represent aspects of the oceanographic community, and she's going to tell us about opportunities for the future and sort of some. And I guess we got a roundhouse discussion this afternoon about we delve in more of where the challenges are, and we're not so interested in identifying a measurement or a widget. We're just trying to understand what the big challenges are in the disciplines and where the gaps are, so that we can start thinking our way through trying to meet those challenges. So with that, I'll hand it over to Tony, who will introduce Sarah.
So it's my pleasure to introduce Professor Sarah Gille from Scripps, UCSD. Sarah is a physical oceanographer whose research focus is on the ocean's role on the climate system. And Sarah got her bachelor's degree from Yale University and then PhD from the MIT and Woods Hole Oceanographic Institution joint program. And then she did a postdoc at Scripps in UK before joining UC Irvine as an assistant professor and then a professor at Scripps UCSD. And Sarah has a long list of awards and honors, and she's a fellow of AMS and AGU, and has got numerous awards. Among them are the NSF Career Award and the AMS Sword of Gold Medal Award, and I will stop right there because the list is long. And Sarah has mentored many students, and she is a co-I on the NASA Earth Venture 3 mission proposal called Butterfly. And she's also the PI for the ODYSEA proposal submitted to NASA's Earth System Explorer programs. And I had the pleasure to work with Sarah on both of these proposals. And so both of the proposals are in the context of the ocean's role in the climate systems. And so Sarah's lecture's topic today will be on that topic. So without further ado, Sarah. Thank you.
Thank you. Thanks. So, yeah, Graham's instructions to me were to think about the future and where we might be headed. And so the instructions came before we knew that ODYSEA was moving to the next phase. So I said I would talk broadly about opportunities for observing air-sea fluxes from space. And this really represents a community discussion that's been going on for a while to think about what the best opportunities are and what capabilities we might be able to obtain. So I want to start with some absolute basics, which is, of course, and this will be familiar to everybody, but the Earth's surface is 70% ocean. This is a water planet. 90% of the water on our planet is in the oceans, and per unit area, the ocean has 400 times more mass than the atmosphere. So the ocean is a really critical part of this. Importantly, the ocean also has, per unit area, 1,600 times more heat capacity. The ocean stores 50 times more carbon than the atmosphere. And ultimately what that means is that as the climate changes, 91% of excess heat is stored in the ocean. About a third of anthropogenic CO2 is taken up by the ocean. So the ocean plays a really critical role in our system. And given how much is in the ocean, it ends up having a direct impact on our lives. The ocean is really what drives disruptive weather. So the flooding that occurred in Texas a couple weeks ago was massive rainfall where clearly the water had to come from the ocean. The ocean and the air-sea exchanges that drive that are really critical. Similarly, all the atmospheric river events that hit California last winter are direct results of air-sea exchange. The same applies to hurricanes. These are 2 hurricanes that came through the Atlantic last August, Idalia and Franklin. We also saw hurricanes that hit the West Coast last year, Hillary and Otis. All of these depend on how the ocean and atmosphere are interacting. The ocean is fueling these storms and making a big difference. So if we think about the big roles the ocean plays for looking at the air-sea system, that some of this is just the ocean serving as a reservoir. The fact that the ocean takes up heat, that it holds an enormous amount of carbon is a reservoir question. And if that were the only thing we were concerned with, we have ways to monitor reservoirs that don't involve satellites at all. In fact, satellites don't do a very good job at seeing what's in the ocean interior. So we do a really good job of asking how the ocean is gaining heat, and to some extent asking how it's increasing carbon content by putting out robotic Argo floats that explore the global ocean. There are close to 4,000 of them available now, and they have very clearly shown the exact role that the ocean is playing in increasing ocean heat content and holding carbon. So that takes us, we tend to think of ocean processes as happening along a continuum. So there are large-scale processes. Here we're looking at a range of spatial scales that go from 10 meters to 10 to the 5th kilometers. And this question of ocean heat content is anthropogenic climate change, global warming, happens over large scales in space and long time scales on the orders of hundreds of years. And so if that's all we wanted to know, we would not need satellites at all. We'd put out a bunch of floats. We'd look at how heat content changed, and we'd be done. But that sort of misses everything else that happens in our system. This large-scale warming doesn't happen without a whole lot of higher frequency and small-scale events that feed into it, which happen on scales here shown, ranging from just a few minutes in time and tens of meters up to long scale. So that includes sort of seasonal scale processes, including El Nino and the Southern Oscillation, monsoons, intraseasonal oscillations, marine heat waves, and faster scale processes, including the diurnal cycle, boundary currents, ocean eddies, mesoscale and shorter scale physical biological interactions, air-sea shelf processes. So this is what we face. If we really want to understand this whole continuum of processes, we can't just look at this anthropogenic global warming. We really need to look at the whole system. And to illustrate that, I wanted to show one example from the Southern Ocean. This is looking at mooring observations from 2 moorings. There are only 2 moorings in the Southern Ocean. It's chronically undersampled. But 2 moorings in the Southern Ocean. One is the Southern Ocean flux site, Soft's mooring, which is south of Australia. And the other was a fairly short-lived US mooring from the Ocean Observatories Initiative. This shows the time series of heat fluxes from these moorings over 4 years when they actually did overlap. And what you can see is that the annual cycle on these is really pretty similar. They're showing the same sorts of warming and cooling. These 2 sites that are very far apart show really similar processes. But if you actually look at what matters for these moorings, or at these moorings, what is controlling heat flux and net uptake of heat into the Southern Ocean, it's happening in highly episodic events. So essentially what we see is that very occasionally, maybe once in a winter, there will be some mass of very cold air coming off the Antarctic continent, a very strong storm, high winds, and that will cool the ocean surface, lead to convective mixing, deepen the mixed layer, and create a situation where you can store a whole lot of heat in the ocean interior. And so what matters is one single strong event per year, perhaps, at each location, maybe a couple. And so that tells us that if we want to understand how the ocean is gaining heat on century scale climate scales, that we really need to actually measure these individual events. We want to understand event-driven, high-frequency processes. And so that takes us to a question where if we want to look at things globally that are high-frequency, event-driven systems, we can't necessarily put out enough moorings to do that. We can't necessarily put out enough floats that sample every 10 days to see those sorts of processes. And that's a real opportunity to look at the system from space. So that says, if we want to look at the whole thing, we need to figure out methods that will let us get all of these spatial and temporal scales all at once. And that's our opportunity to really look at how the ocean and atmosphere are interacting, taking advantage of satellite resources. So I want to then spend a moment talking about, so I've talked in general about how important it is that the ocean and atmosphere talk to each other and how air-sea fluxes really drive the weather that we experience on land and a lot of our climate system. But I want to talk about the specific types of air-sea fluxes. And I'm going to violate all the rules of giving a talk and give way too much in equations and technical detail. Oops, but let me back up. So there are basically 4 categories of air-sea fluxes. There's momentum flux, that's the wind driving the ocean. There are heat fluxes, that's thermal energy going into the ocean and coming out of the ocean. That happens through radiation and other processes, which I'll get to. There are freshwater fluxes, evaporation and precipitation, and there's gas exchange, how much carbon dioxide or oxygen is taken up by the ocean. So if we look at them, these all go with equations, and this is where I'm violating all the rules of a talk. But I want to talk about what makes these work. So if we think about momentum exchange, that's a stress at the ocean surface that depends on the horizontal velocity and its correlation with vertical velocity. We are terrible at measuring vertical velocity from any system. But that's what's driving wind stress. And then we also talk about wind work, how much work is put from the wind into the ocean, which is a dot product, so another correlation of wind stress with ocean surface velocity. Heat fluxes come in multiple categories. So they're short wave energy coming in from the sun, long wave radiation, that's black body radiation, which can come from clouds beaming energy back down to the ocean. It can come from the ocean having black body radiation emitted from the surface and going back out towards space. And then there are sensible and latent heat fluxes that depend on correlations between vertical velocity and temperature, or vertical velocity in the atmosphere and humidity. Freshwater fluxes include precipitation, which is measured from satellite precipitation missions and other things, and evaporation, which is, of course, directly linked to latent heat flux. And gas exchange is also a correlated quantity related to the partial pressure of gases in the atmosphere and vertical velocity. So we've got all these quantities that depend on covariances. And I guess I want to say there's some that I've marked in blue here. Those are things that are not covariances. And we have fairly clear ideas of how to think about measuring them. But everything in red is a covariance of something that depends on a vertical velocity that we don't know how to measure. So that's a challenge. And what people do, so you can directly measure fluxes. And for moorings, that is roughly possible. So here's a sample of moorings. Some of these have managed to have direct covariance systems put on them. But in practical terms, even from a mooring, it's really hard to measure that direct covariance between vertical velocity and other quantities. And so in practical terms, what people do is to take advantage of what we can measure: humidity, wind speed, currents, temperature, and then do the best we can. And that involves creating what's called a bulk parameterization, which takes advantage of variables we can measure and says, let's just find products between these. So I realize I've got subscripts that have been lost here, and I apologize. But so if we want to look at wind stress, then we can ask, what's the horizontal wind, which we are able to measure, and how does it drive things? And then there's a drag coefficient, CD, that determines how that translates into a stress. Sensible and latent heat flux have similar structures. They depend on the wind speed multiplied by the difference between air and ocean temperature, or air and ocean humidity. And gas exchange, gas exchange also depends on a difference between ocean and atmosphere, partial concentrations of gas, or partial pressures of gas. So I need to point out, although these all have wind in them, all these red equations, it's not actually wind that matters, it's wind relative to ocean currents, and I'll come to that in a moment. So, so what I want to do is, so we actually need to represent these with the difference between the wind speed at the surface, or wind vector wind at the surface, and ocean currents. So that's really critical to actually understanding how these work. Now, that leads to an interesting point, which I'll come to in a moment. So there's been a lot of community discussion about how to get at air-sea fluxes. The oceanographic community, as many of you know, does a decadal exercise called Ocean OBS. So the most recent was Ocean OBS 19, which involved putting together a whole menagerie of community papers that documented what people think are the priorities for an ocean observing system. And in 2019, there were an enormous number of those papers that addressed air-sea interaction, and that led to an outgrowth of Ocean OBS 19 was OASIS, Observing Air-Sea Interaction Strategy, which has been an effort to put together the community needs for air-sea interactions. So the OASIS effort started with an effort reading of all of these community papers, categorizing them into different groups, and trying to identify what the community priorities were. So the first of those, which led to what OASIS calls grand idea number 1, was that we actually need in situ observations. So it's critical to have a globally distributed in situ air-sea interaction network of observations that we can use to measure air-sea fluxes. And this put together a vision of something that might look like this. So what you see is the global map of air-sea fluxes, approximated net air-sea flux. Some large black squares, which show places where you might imagine having really high quality super sites that measure flux covariances, that have excellent measurements of all of the possible variables you could want to understand air-sea fluxes. And then a bunch of gray dots, which try and fill in the gaps. But you can see that this is an enormous observing system, prohibitively expensive, very hard to manage maintaining it. And B, it still leaves a lot of structure that is not going to be sampled. And so that really leads to a need to come back and say, okay, how do we knit that together? So OASIS has identified grand idea number 2 as a need for satellites optimized to look at air-sea fluxes. And that's a real opportunity for NASA's decadal survey to say, okay, how can we address these fundamental needs for society in looking at air-sea fluxes? OASIS also has identified a grand idea number 3 to improve models, understanding of processes that feed into air-sea interaction, and as well as an overarching grand idea to make sure that data are available to stakeholders around the world through an integrated system. So, so we come to then asking, what can we do from space using these bulk parameterizations and variables that we can realistically measure? So this is where we're going to talk about what the opportunities are. So when we talk about momentum, that's the sort of thing that ODYSEA, measuring winds and currents, has the potential to look at. For heat fluxes, the butterfly mission that Tony mentioned, is aimed at getting at the turbulent part of the heat fluxes, the red equations, measuring using the bulk parameterizations. And that would, of course, feed into looking at evaporation as well. And for gas fluxes, there's been a little bit of talk about how to get at this. JPL was part of a proposal for Earth Ventures called SOS Zephyr that was aimed at just getting a really good handle on the wind speed part of this. But there's not really a strategy yet for how to deal with the gas concentrations. And so we'll put that on hold for now. So I'm going to talk about a series of things today. I'll talk about wind first, then heat flux, then momentum, the momentum part, and I'll save for another day the questions that are in blue, radiative fluxes and precipitation, and the questions about gas exchange. But I wanted to start just with wind because it appears everywhere in this process. So let's start with wind, the red terms here. And I'll just remind you how we measure wind from satellite. So the basic idea is that, and it's important to test this out if you're looking at a pond or the ocean. If there's any amount of wind, what you see at the ocean surface and what this photo shows are small centimeter scale waves that are called capillary waves. They depend on surface tension. And the fortunate thing about capillary waves is that they are aligned consistently relative to the wind. So that means that if you take multiple looks at the same patch of ocean, you get different amounts of backscattered radiation depending on the angle of your radar relative to the angle of the wind. So that's what scatterometers do. And that gives us a way to back out both the wind speed and the direction. So really critical for understanding what's driving the ocean. There also are passive instruments, Cover among them, and I think Shannon Brown is here, that don't use an active radar but are still able to pull out information about both wind speed and direction using the emitted radiation. So the critical thing is that we are talking about relative winds, and I wanted to pound on this point a little. If we measure winds, so you can imagine looking at a large-scale wind, which is these yellow vectors blowing over an ocean eddy, like this circle here. And what you can tell is that if the wind is blowing on the north side of this eddy, where the wind is blowing opposite in direction to the ocean current, that means that the wind and current are countering each other. That makes the effective stress on the ocean surface greater. On the other hand, on the south side of this eddy, the wind and the ocean current are moving in the same direction, and that means that the wind and current are working in the same direction. There's less effective wind on the surface. So we actually really need to, we want to understand the wind relative to the current in order to get this under control. Now, the capillary waves, what every satellite measures, depend on relative winds. So if the only way we had the only tool we had in our toolbox to measure winds was using satellite data, we would not be talking about relative winds. We would just measure what the satellite sees. That would tell us about something that was wind stress, and we'd be done. But the problem is that we actually have to calibrate our satellites and understand how things work. And every in situ measurement we make measures absolute winds relative to a point. So in order to figure out what winds mean, we actually have to look at, we actually need to understand winds relative to currents. Otherwise, we would not be able to tease them apart. So that's where we are. Now, measuring winds, there are a bunch of satellites that are destined to measure winds. So I pulled this table from the World Meteorological Organization. And what it shows is a list of all of the global satellite wind measurements that are available and timelines. This is looking from 2024 forward for the next 10 years. So you can see that there are a bunch of measurements available. It's useful to think about who's flying these measurements. Many of them are Chinese. We don't have access to those in the US, so I blocked them out. Some of them are passive. two of them are Russian. I don't know what our access is going to be for those, but let's assume that's a problem too. Some of them are passive. They're great, but they don't achieve the same resolution you can achieve from an active scatterometer. And so what we're left with is not so many missions, some big gaps. And if you look at the time of day they sample, these are sun-synchronous missions. They're at 9:30 a.m., 9:30 p.m., and noon. And that's it. So this is a bunch of European missions and then a couple Indian. There's nothing in the US. And we see big gaps moving forward. So that really says we have an opportunity, if we want to understand how winds evolve through the day, we have a big temporal gap. And if we want to understand, if we want to have a US contribution to this, there's an opening. So that's wind. I want to talk now about heat flux and the butterfly concept. So heat fluxes, as I said, depend on a bunch of variables. Both the radiative fluxes, which we're not going to address, and then latent heat flux and sensible heat flux. And all told, that's 7 or 8 variables we need to measure. So some of them, before I get to butterfly, I want to talk about SIMR, which is a European Space Agency mission that is scheduled to launch maybe next year, maybe not that soon. But it's a new microwave radiometer that will provide, by using a very large antenna, will provide much higher resolution, sea surface temperature, ocean wind speed, salinity, sea ice concentration. So about 15-kilometer resolution for sea surface temperature. This is a big improvement over other microwave systems. And let's see if we can get this to go. So it's in development with the European Space Agency, and it will provide new measurements and potentially the opportunity to think about how we integrate with SIMR in doing operations on the US side. Butterfly was proposed a few years ago as an Earth Ventures mission, and it is slated to be reproposed when an opportunity next appears. So it's aimed at measuring all of the terms we need to get at the bulk parameterization to look at air-sea turbulent heat fluxes, latent heat flux and sensible heat. So that requires measuring, and it's aimed at getting fairly high resolution, so with the real hope that you can see what fuels a storm as it evolves over the ocean and how it moves, what's making the ocean and atmosphere interact. This is a lot of detail about butterfly, but what I want to emphasize is the really critical thing that butterfly offers is sampling enough microwave channels to be able to get bottom of the atmosphere temperature and humidity. So to really be able to tease apart the air-sea temperature and humidity difference in a useful way. And it's achieving that with spinning reflectors, aiming at 20-kilometer resolution. So, and then from there, I want to move on and talk about momentum fluxes. And that's what ODYSEA is aimed to do. So that's what we're working on very actively over the next year to get our next phase of the Earth System Explorer proposal worked on. But before I talk about ODYSEA, I want to talk about what else is happening. So ODYSEA is aimed at doing global measurements. The European Space Agency has a different approach to get at some of the same variables. It's a synthetic aperture radar system called Harmony, aimed at measuring wind stress, currents, waves, sea surface temperature, and more. It's based on a SAR system. It uses a Sentinel SAR and then adds in 2 extra receivers in order to get multiple looks at the same patch of ocean. So it's from that able to get surface motion, currents, surface winds, analogous to scatterometry, and wave spectra, as well as the skin temperature. So it's like having a bunch of current sensors, anemometers, and measurements for air-sea fluxes. Harmony is scheduled to launch in 2029, and some things to know about it. One of its targets is in fact the marine atmospheric boundary layer. It's aimed at getting the upper ocean with high resolution, but it is SAR-based. It is really measuring tiny vignettes, 20 kilometer by 20 kilometer patches of ocean. So it's really targeted at something that looks like the submesoscale, what we might otherwise get from an airplane, and not what we get from a global satellite mission. And the community has identified that there's some challenges ahead for Harmony in finding the retrieval and developing CalVal. Most of the processes from Harmony will be measured infrequently. There's a 12-day repeat. They're only targeted patches of ocean. I see a hand.
Yeah, just quickly, Sarah, is it the same little regions that are being sampled, and how frequently are they being sampled?
It's not clear. It's sort of opportunistic because it's using an existing SAR system, and it looks like the SAR is targeted at distributed patches depending on what users request, and so Harmony will get these currents and winds in distributed patches in the same way. So it's going to be a little bit patchy, I think.
So do you get global sampling, true global? Even over a long time period, you sample all the ocean?
You have the possibility of sampling all the ocean, but you will not get a global picture of anything. I think it's useful to think of something like this as being a lot more like having an airplane you're allowed to fly a lot. So, and just for completeness, I wanted to point out there was another proposal to the European Space Agency called SEA-STAR, also SAR-based, focused specifically on getting really high resolution measurements by focusing only in coastal areas. So specifically targeting getting fast evolving coastal ocean dynamics at very small scale, 1 kilometer scales, but trying to get one-day repeats by only targeting the same patches of ocean. That was not selected. So that was in competition last October for the European Space Agency's Earth Explorer 11, and it was not selected. They're looking for, Christine Goman-Ginger, the PI for that, is looking for other opportunities. And so that takes us to the question, what if you actually want to see things globally? What if we want to understand how storms evolve? And that's what, for that, you need something that has a wide swath, a daily repeat, where you can really come back to the same patch of ocean every day. And that's what ODYSEA aims to achieve. So ODYSEA is measuring surface currents and surface winds with a sampling that will show us daily, give us basically a daily revisit. So I want to talk a little about what ODYSEA aims to do. It is a Ka-band Doppler scatterometer, and it's intended to provide, first of all, the first ever global measurements of total surface currents. We have measured surface currents in a lot of ways, but never with something as global and complete as what ODYSEA can do. And along with that, it measures ocean vector winds. The technology behind ODYSEA is taking advantage of a scatterometer, so pulsing a radar signal down to the ocean surface, measuring the backscattered radiation, but also saying that ocean surface is moving, and so that will lead to a Doppler shift in the radar signal. And if we measure that shift in radar signal, we can tell what the currents are doing. So it's two different measurements, the backscattered energy and the Doppler shift of that of the wavelengths of that energy. And in both cases, relying on getting multiple looks at the same patch of ocean in order to be able to back out total currents. The mission is set up with two science objectives and an applications objective. The science objectives are focused on wind current coupling, on surface current exchanges of eddy kinetic energy, how currents evolve in response to wind. And the applications are focused on providing near real-time data that will meet the needs of weather forecasters, maritime operations, and a variety of agencies. So I want to give you a little picture of what ODYSEA will deliver. First of all, if we think about wind currents, it's useful to think about gradients of wind because those are really critical for ocean dynamics. And ODYSEA's measurements go from what we currently have in our program of record, a fairly fuzzy view of wind stress curl, to something that will pull into focus lots of structure that is very detailed and will give us a much better picture of how the ocean is moving. In terms of ocean currents, as I said, our current picture of ocean currents is incredibly fuzzy. We don't really have a strong sense of what ocean currents do. We pull that together from a variety of observations. ODYSEA will give us a very structured, filamented view of what surface currents are doing. So a big change in what we can see. And so the science hypotheses for ODYSEA are focused on understanding this. One of the things that we're very interested in a changing climate is asking how surface currents might respond to changing properties of the ocean. The one hypothesis that has been put forward in a number of climate papers is that in a changing climate, the mixed layer of the ocean will change. We expect that the mixed layer will go from being deep to shallower. And if that has the potential to mean that you can accelerate ocean currents much faster, and you might expect to see much stronger currents. Now that could happen on a century scale, but it's also something we can look at on a seasonal scale. As you change the mixed layer, how do ocean currents respond? Now, so that's an interesting hypothesis. It merits attention. The other interesting aspect of this is that the community has no consensus. So another hypothesis says that as you deepen the mixed layer, you change how the ocean stores potential energy. And here we're looking at the Kuroshio extension region in the Pacific Ocean. End of winter, you can see you expect to have a deep mixed layer, so you might expect slower currents, but in fact we see much more kinetic energy. At the end of summer, when we have shallow mixed layers, back that up a moment, we see much less kinetic energy. And so that's an argument that by having a deep mixed layer, you're actually able to store more potential energy, and that potential energy can be converted into kinetic energy, so it leads to this faster motion in winter conditions. So the community is arguing about these. ODYSEA will give us the opportunity to really explore this in much greater detail over a range of scales and ask, when does one apply, when does the other? The second issue, science objective, actually the first science objective for ODYSEA, asks about how winds and currents couple together. And this is again a case where the community has put forward a whole range of hypotheses. In running coupled ocean atmosphere models, people have said if you have a prevailing wind and you ask and a prevailing current, how will those interact? So one set of studies says there really should be no impact on winds. Nothing is induced. There's no vertical motion. The current and winds basically don't have any meaningful interaction. Another set of studies say that the interaction between winds and currents is completely local. It is just directly over the current, and it doesn't spread. And a third set of studies say that there are both local and remote interactions between winds and currents. So the winds blow, currents move, everything is completely integrated. To pull those apart, ODYSEA will be the perfect tool to really let us look at how these interactions work. So ODYSEA is also set up to meet operational needs by providing near real-time winds and currents, to let us look at storm evolution, surface waves, maritime safety, debris transport, supporting NOAA, the Navy, the Coast Guard Search and Rescue, the French Mercator Ocean International. It's actually not just French anymore. And so you can see where ODYSEA falls in space and time for winds and currents in these two figures here. This is showing winds. You can see ODYSEA is providing, over 2 days, 90% global coverage, much greater coverage than we get from existing scatterometers, and much more missions like Harmony and SAR missions and CSTAR provide high spatial resolution, but with very infrequent coverage. So ODYSEA is in the sweet spot of providing high spatial resolution and frequent coverage. And for currents, nothing has provided this sort of frequency of current that we expect to get from ODYSEA. It also is providing total currents moving beyond the geostrophic component only that we see from SWAT and other satellite altimeters. So really new observations. A quick overview to summarize. There are currently no sensors on orbit that measure total surface currents. There's no US operational scatterometers to measure winds. So ODYSEA takes advantage of an existing airborne Doppler scatterometer to fill this gap for both these needs with 90% global coverage and the capability of providing near real-time measurements. So, oh, and I didn't get that last statement corrected. The proposal was submitted last summer, and our next proposal will be due in March, I think. So just to put this all together, we have this range of different fluxes we look at, from some of which we can get information from existing satellites, but there are lots of gaps. They're not really meeting global daily needs. There's some things that are funded and will move ahead, and there's a lot that will be possible if new missions are funded, both to get turbulent heat fluxes and to get momentum exchange between the ocean and atmosphere. So the real opportunities to ask about how to put together a portfolio of satellite missions that will measure the whole suite of air-sea interaction. So if we come back to this diagram trying to spread out all the processes we look at over space and time, you can see that different satellite missions fill different parts, different sectors of this sort of diagram. They're really emphasizing complementary space and time scales, as well as complementary measurements. And so there's a real opportunity as a community for us to think, how can we build a constellation of satellite missions that will let us ask how the ocean and atmosphere interact, that will give us the information we need to build forecast systems that help our land-based weather, our maritime operations in meaningful ways. So if we envision the next decade of air-sea flux observation from space, we might imagine looking at momentum exchange across a range of scales by coupling Harmony's 20-kilometer vignettes with ODYSEA's global coverage. We might imagine looking at turbulent heat fluxes from multi-channel microwave systems, Butterfly, maybe taking advantage of some of Simmer's capabilities to expand temporal resolution, and to really be able to look at event-driven heat exchange. And we hope to be able to get wind measurements throughout the diurnal cycle so that we can really watch storm evolution and characterize diurnal wind variability. It would be great to have surface waves. SAR capabilities might get at that. There's some other options. And of course, anything we do, we want to have near real-time data so that we meet operational needs. So, and finally, I have to say that there's ample opportunity to continue this discussion. For ODYSEA, we are actively inviting the entire community to get involved. There's an ODYSEA simulator. It's available from our website. So anybody can play with it, test out ideas that you think are important, ask what's possible, and of course, we want to hear about it. That'll help us make the case for the mission. And more broadly, to discuss the science of air-sea interaction from space, OASIS's grand idea number 2 is coordinating the air-sea fluxes from space webinar, which takes place Tuesdays at 8 a.m. Pacific time. You can sign up from the OASIS website, and we'd love to have people involved. So it's really important to have an ongoing community discussion. So I'll end there, and I'm happy to have discussion and questions.
Hi, Eric Leroy. Just probably a stupid question, but with SWAT and SSH, very high resolution variations, can you just not backtrack the wind using some kind of inversion?
SWAT, yeah.
Oh, sorry, the current, not the wind.
Oh, current. You can get geostrophic currents from SWAT, but there are 2 limitations to that. First of all, SWAT has a swath that's about 120 kilometers wide. So it's really great for getting geostrophic currents within the swath, but it won't provide daily coverage. But the other challenge with geostrophic currents, and one of the things we really learned in the 10 years we've spent working towards SWOT, is that geostrophy depends on what's called balanced motion. It depends on the Coriolis effect, and it's a process that works on scales larger than some scale. You know that the Coriolis effect doesn't matter in your bathtub. We know that it matters on a planetary scale. And that transition from bathtub to planetary scale happens somewhere. And it looks like it happens around 70 kilometers in much of the global ocean. So SWOT is great for getting geostrophic velocity for scales larger than 70 kilometers. At scales smaller than that, the geostrophic component of velocity is embedded with a whole lot of other motions, which are really exciting. But they include tides, internal waves.
So it becomes an attribution problem?
Yeah, so we have more to learn. Putting these two together, ODYSEA plus SWOT, would be incredibly powerful.
Okay, thank you.
Any other questions?
So you mentioned regarding the RC fluxes, a lot of the microwave possibilities, but hyperspectral infrared and radio occultation can actually provide information about water vapor and temperature much closer to the surface than microwave in general. Radio occultation can sometimes provide, water vapor and temperature 200 meters above the surface. So what do you see the role of hyperspectral infrared and radio occultation in the air-sea turbulent fluxes of heat and moisture?
I should have said, ideally, what the in situ people want is measurements at 10 meters above the surface, or maybe 2 meters above the surface. So we're really pushing the limits. I think that as we look towards the future, the question is, how do we get the best measurements? And so if radio occultation and hyperspectral systems can do it, then that would be the direction to go. I don't think, so far, the analyses have suggested that microwave profiling is capable of doing this, and that's a good strategy. But as we look towards the next decadal, I think that's a good open question. What are the best ways to get the right measurements to really understand the marine atmospheric boundary layer?
And just not to don't monopolize, but the PBL incubation studies that have been going on and have been recommended by the decadal survey, the sort of surface fluxes are a key component of that as well. And I think one of the realizations of the community is that it has to be a combination of different technologies that will get us where we want to be in terms of PBL, temperature and water vapor structure, and probably, as you say, for air-sea fluxes, for the turbulent heat and moisture exchanges, it has to be a combination of technologies as well. Thank you.
Yeah, so I think this is a really important discussion, and that's one of the reasons we've tried to make sure that there's a community webinar that really gives an opportunity to have lots of people talking about this.
So you focus a lot on the observation system, rightly so, but as NASA's moving towards more Earth action, can you say a few words about sort of the state of the art in terms of comprehensive models that are tailored to decision support, and how they may go forward to try to integrate all these observations?
Yeah, I think one of the really important things to recognize, I mean, air-sea fluxes are intimately tied into Earth action because this is feeding the bottom of the atmosphere. But modern forecast models, what ECMWF runs and other forecast models, are fully coupled to an ocean. And so they're really depending on understanding how the ocean and atmosphere are feeding information in between each other. So measuring fluxes enough to make sure we understand the processes is a really important part of this. So I see this as sort of something that should be at the forefront of any Earth action.
Okay, so Sarah, very interesting concept, thank you. I want to come back and talk a little bit more about the subject that Randy brought up, and that's operational. From the standpoint of the proposal itself, is there an approach being made by you or within the community to try to bring, let's say, specifically NOAA into the fold here and get them to be a part of the proposal?
For Odyssey, NOAA, we have NOAA participants on our science team, and and we're talking even more extensively with NOAA about what they can do and how to make that work. For Butterfly, it was the same. It is really important as we talk about these types of missions to make sure that we're figuring out how to build that bridge to operational applications and to the stakeholders who will use it in the near real-time capability.
Well, and specifically for NOAA, in the past, they've gone in, let's say, on EVs and actually said, hey, if something was worthwhile to us, we might put some money into the program. And it might be worth your while to make sure that they're included in the community discussions. We've already started approaching some of the management in NOAA to see if they'd be interested in participating in the program.
That's a good point.
Thanks for the nice talk, Sarah. Are there components of an in situ observing array that would be useful to couple with ODYSEA? And I'm thinking specifically maybe Argo with an adaptive sampling program where they sample more rapidly when there are interesting events happening.
That's a really good point. I think the first thing that we've been talking about is we've seen the success of adopt a crossover for SWAT, and so there's really an immediate discussion. We don't expect ODYSEA to have a 90-day period with an unusual orbit when we would want to have an absolute global targeted observing system, but how can we feed on that energy and that excitement of getting a global community involved to get some of the in situ measurements that would help understand what ODYSEA achieves? And so there's been a lot of discussion within OASIS about working with the USVs, uncrewed surface vehicles, to try and get measurements that would be useful for calibrating, validating, putting a complete picture together of what ODYSEA is measuring. Profiling Argo floats could do something similar. I think it's really important to have this discussion. If ODYSEA moves forward, building a community that will be ready to ask how do we get the best validation and calibration is an important part of the success of the program. And there's a proposal going to US CLIVAR to do a USV workshop where we're hoping to get this pushed in as one little detail.
Sure. So to build on Randy's question about the modeling, the satellite sampling and in situ will always be subsampled in time and space, right? We'll never have complete, and so there'll be modeling assets to help fill in time and
Right,
space.
yeah.
Can you comment on where the pillars of those assets are in the community? I mean, say, for example, is it ECHO, or how is it ECHO with other assets? Where are the chief modeling pillars that will fill in that time-space stuff for either operations or just science?
Yeah, so there are operational aspects. So for ocean currents, the Navy runs an operational model that directly impacts what they do. They are part of the ODYSEA science team. And the Navy model then feeds into Coast Guard search and rescue, so there's sort of a continuous chain there. For NOAA and for other weather agencies, they're pulling on near real-time data and using the data. They're used to using satellite data when it exists and putting together a complete picture. I think on the science side, there's some interesting questions. How do you push the limits by doing things that are more exploratory? And that comes through programs like ECHO and some regional modeling using the ECHO formulation. And I think that's going to continue to grow in the coming years. But yeah, you raise a good point. There is a large gap here of high-frequency processes that we don't have ways to get from satellite. We can get them from moorings, but then we only have a single point. And so those are challenging places to observe.
Any further questions? Okay. So if I may expand on Sarah's comments on how ODYSEA and Butterfly engage the operational community in the context of Earth Science to Action. We have operational partners from NOAA and NASTIS who work closely with the National Hurricane Center for the ODYSEA wind. And for the currents, we work closely with the Naval Research Lab operational data, couple data simulation for the wind and currents that support a wide range of users, including the Coast Guard. And the French partner, the Mercator Ocean International, they take the current data can produce ocean forecasts that support EU effort. So it's an EU mandate. That's why they call it Mercator Ocean International. It's no longer a French organization. And for butterfly, we actually have National Weather Service collaboration and endorsement letter from National Weather Service for directly incorporating those data into the couple simulation for weather forecasts. So those are our partner for related to the Earth actions.
Well, actually, Tony, can I ask a question on that? So as we were talking Earth Action and with the partners, which is excellent, have you guys had some pushback from those partners? Because this is very cutting edge, but there's not necessarily a follow-on already being discussed. So is continuity an issue for some of the partners to really be taking this data, changing their system, because obviously that's some kind of financial burden sometimes. Have any of those conversations come up? We've heard it with other partners for some of the first, premier scientific observations that could be operational, but since there's not a direct funding line like, our European partners, sometimes it's a little bit harder, it seems, for them to commit.
Yes, those conversations come up. But scatterometry, people know how to use, so there's no concern with that. Surface currents for ODYSEA is new, and we have been told don't expect anybody to use it right away. Make sure the mission lasts long enough that you give people time to get to the point where they can be trying to use it operationally. This is viewed as a demonstration project, and I think part of our messaging is these are science missions. We're going to see what's needed, what works, and use that. The vision would be to use that to define a future observing system.
Just following on Michelle's question, the fact that it's more cutting edge brings up the question of, as you're going through step 2 with ODYSEA, are you going to depend or can you leverage anything that's going on with S-mode and the airborne campaign over the next 9 months, or are the timescales too far different for their data analysis to help your proposal?
Well, the S-mode lead, Tom Farrar, is on our science team, and a very pointed message went out to the S-mode community saying, get your papers out. So we expect to use S-mode where it's useful. In some ways, S-mode is getting at sub-mesoscale processes, more at the scale that you might get from Harmony, and so S-mode may open some doors to other types of analyses in the future, but for ODYSEA, the fact that S-mode data works, the problems they encounter, the questions, is a really important part of this, and that's what we're going to make that work as best we can in the next 9 months.
There's a question online from Angelica Rodriguez. Much of the motivation for observing these fluxes is to move towards their representation in climate models. Can you comment on the vision for making that leap?
Yeah, so I think I want to think about this as the full weather to climate continuum, but we have parameterizations for these fluxes based on bulk parameterizations with drag coefficients we don't trust necessarily. We would like to get everything to be much better, and to do that we need a lot more measurements. So by making the types of measurements we can make with ODYSEA and Butterfly, we can get a much more extensive set of observations, look at where, although I showed you these bulk parameterizations, we actually want to look at where things don't quite work and figure out how to refine the representations so that we have a better understanding of those processes. Coupling between ocean and atmosphere has been a challenge at all scales.
Thank you. So we have one last question. We are top of the hour. Jimbo?
Just quickly, Sarah, follow up with Eric's question. Assume SWOT will live long enough, or there's a SWOT follow-on that cover the same period. Do you see a synergy between ODYSEA and SWOT, and on what area?
I think it's one of the most exciting synergies for super things that are really hard to explain to the general public. But when we talk about, I think one of the questions that is driving a lot of SWOT science is about how to distinguish balanced motion from unbalanced motion. And if you have SWOT plus ODYSEA, you have the tools to put that together. in a really exciting way.
Okay. Thank you so much,
thank you.
Sarah. Let's thank Sarah again. Thank you.